Okay, so let's talk about similar triangles here. I've drawn two triangles. It's possible they're similar. We're not 100% sure yet. We got to take a look at some of this information, okay? For simplicity's sake, we'll just say they're both right angle triangles, so that this angle is the same. Normally, when you look at a similar triangle, depending on the level of math you're in, they may give you an actual value, so they may say something like, oh, this is 35 degrees, and this is also 35 degrees, okay? And if you have two angles the same, that means the third angle must be the same. And in a triangle, all angles, so let's call it, we won't use those variables yet. We'll say angle 1 plus angle 2 plus angle 3 must equal 180, okay? We can quickly plug in values, okay? And we'll just say, A3 is the one we're not sure of. We'll use a little algebra. We get A3 is equal to 180 minus 90 minus 35. That would be 90 minus 35, which is about 55, I believe. Okay, so we found the other angle to be 55 degrees. That's nice. Sometimes what they'll do instead is they'll represent those. Let's see if I can just do a quick copy of it. There we go. Nope, that did not do what I wanted. Try it one more time. See. Oh, here we go. Hey, that's what I want. Nice. Okay. And do the same here. Little duplicate. Okay. Sometimes they'll represent this information, not with numeric values, but they'll use a variable. Okay. And as long as the variables are the same, the concept is that that variable must equal the same amount as something else. So you may have seen this one. They'll call it theta. They'll sometimes use another one called mu. They're just they're letters of an alphabet, just not the alphabet we use. They're Greek alphabet letters, and there's uppercase and lowercase. Instead of using X and Y, you can always use those, but we tend to use Greek letters, at least in lower level math, to represent angles. Okay. Yeah. So the reason I've done this is to show us that if all the angles of a triangle are equal, okay. So we'll say like the angles of triangle 1 are equal to the angles of triangle 2. That means they are similar, okay? They're similar triangles. So similar triangles aren't congruent. Congruent would be like the same thing, but similar triangles are triangles that have the same angles and their ratio of their side lengths are the same as ours, okay? So for instance, I'm going to give us one here, and you're probably going to end up using one like this. Ooh, I want to erase these angles just because I want to touch on something else that we'll eventually start working with. So I'm going to change the angles just slightly to make it more along the lines of a triangle. This is actually considered a special triangle that you may be more familiar with. I'm going to say that this one here, I've kind of drawn the angles wrong. This one side is the distance of root 3. This one is 1, and this one is the length of 2. Okay, so I'm going to use that as the length. Then for this similar triangle here, what we'll say is that this one is actually, let me give a nice value that's easier to work with. We might say that this is root 2. No, let's say it's 2 over root 3 is the distance of it, okay? Oh, what am I saying? No, there's a really nice one I should use. What am I talking about? Okay, oops, that's not the number. I want to use 1. We'll say the length of this hypotenuse is 1, okay? For similar triangles, we just have to find the ratio between the equivalent sides, okay? All of these sides are technically different lengths, so they might label the triangle something like this. You may remember from like elementary school, they call it scalene. They're all different. They all are different in this case. But the length of them are really important here. So this one has a length of 2. This one has a length of 1. Because the angles are the same, there's going to be an equivalent ratio. In other words, there's going to be some value that we can multiply by that'll take us back and forth, okay? Now, a lot of times we think of going down. So for instance, if I start from this one and I said, what value would take me up to 2? Well, I'd say, well, from 1 to 2, that's pretty simple. I can just multiply by 2. And if I need to do the algebra, I can say say 1 times what value equals 2. I divide by 1, x is equal to 2. Great, that's our ratio. And then a lot of times the reverse of that would just be the concept of dividing by 2. But we can always actually only use multiplication if you like. You don't have to use division. And instead of saying divided by 2, you can actually multiply by the reciprocal, 1 over 2. That's actually the same as dividing, okay? So we'll say we multiply by a half. So that means to go from the number 2 to the number 1, you either divide by 2 or you multiply by 1/2, okay? So in order to find out these unknown sides here, we are going to take the values of the sides that are equivalent or they're in the same part of the triangle for us, right? So I go to 60. What's my adjacent side to 60? What's the adjacent side to 60 here? So this one is 1. So I need to get over here and I need to divide by 2. So 1 divided by 2, I can write it as 0.5, or I'm actually going to leave it as a fraction because these fractions come in handy for some of the trig you're going to do in the future. This is a specific triangle, okay? So with that being said, I do the exact same operation over here with the adjacent side of 30. Okay, this one is root 3. Well, I can either multiply by a half or divide by 2. Same outcome, and I would get root 3 over 2. Now, I know those aren't values that make sense to us on like a number line. Root 3 over 2, oh, what is that? It is a number, probably like, I don't know, 0.67, something like that. But we're going to keep them in this form because we want to use rational numbers. We're trying to use rational numbers where instead of using long digits that technically never end and we have to write out these very long decimals, these values become important for something called the unit circle, which we'll use a little later, okay? I'm going to jump down to this one down here. This one's a little more ambiguous. We don't know the angles of these triangles, and remember, they're not to scale. I know that you saw me copy them, but let's assume they're not to scale, that these two triangles down here, they're not equal to each other, okay? I'm going to tell you something about this triangle. I'm going to say that it is isosceles, okay? And the distance here is 1, and the distance here is 1, okay? So we're going to do a little bit of Pythagorean's theorem to help us solve this, and then try to figure out the similar triangle property, okay? So if this is 1, and this is an isosceles triangle, that means this side must also be 1. In other words, the lengths are the same. And then I have to find the hypotenuse. Well, if we do a quick Pythagorean's theorem, we know that c squared is equal to a squared plus b squared. C squared is equal to 1 squared plus 1 squared. I'm running out of room here. C squared is equal to the value of 2. So c is equal to root 2. So the hypotenuse here is root 2. Now that I have the hypotenuse, I can find out the ratio for these two similar triangles since all the angles are the same, right? Theta and theta, mu and mu, right angle and right angle. Okay, I know these triangles are similar. How do I go from this to this? Okay, well, to go from root 2 to 1, I can divide by root 2, or I can multiply by 1 over root 2. So we're going to take the associated side. What's the adjacent to mu? Well, it's 1. And if I divide it by root 2, I would get 1 over root 2. Same idea here. Technically, it's isosceles, so I already know the answer, but we're running out the same process. 1 times 1 over root 2 would give us 1 over root 2. I chose these because these are actually special triangles. And it turns out if these are isosceles, that also means if this is 90, that the angles here must be 45 degrees and 45 degrees. And you can kind of solve that for yourself by going through that little formula of the 180. But this is the idea of similar triangles. There's one other relationship in similar triangles, which we'll very quickly try to solve, okay? And it has to do with area of similar triangles, okay? I want to scroll down just a little. We'll use these two triangles, so we'll keep them in the picture. But if I find out the area of the first triangle here, I'm going to call it triangle 1. Because it has a right angle, this is really nice. I can use the area of a triangle, so I'll call area of the triangle number 1, I'll give a little subscript, is equal to the base times the height And that would give you a square, right, or a rectangle. And I just have to divide it by 2 for the triangle. That's the area of it, okay? The base happens to be 1, and the height happens to be 1 here. So we get 1 times 1 divided by 2. Okay, so it's 1 over 2 units squared. I didn't give it centimeters or meters, so I'm just going to say units for now, okay? This one here is a little trickier. We're going to do some radicals to figure this one out. Area of the second triangle is equal to still base times height divided by 2. Base happens to be 1 over root 2 times 1 over root 2, all divided by 2. Little tricky, so let's focus on the numerator here. I'll put a note on the side for my calculation. 1 over root 2 times 1 over root 2. We do numerator times the numerator, that's 1. And what's nice about this is the root 2 times root 2, that actually just going to be the value of 2. I don't know what root of 2 is, but I do know if I multiply the 2 together, because of square roots, that is 2. And if you want to see the exponent part of that, it's the idea of, technically this is 2 to the half times 2 to the half. And when you're multiplying exponents, you keep the same base. If they have the same base, you just add the exponents. A half plus a half is 1. It gives me that value of 2, which I found. So now I have 1 divided by 2 over 2. I'm going to rewrite this so it's a little nicer to look at. This is the equivalent of saying 1 over 2 divided by 2. And if you remember fraction rules, we can just turn our division when we're using fractions into a multiplication question. So 1 over 2 times, and we just find the reciprocal of this, 1 over 2, which is going to be equal to, need a little more room, 1 over 4. So we get 1 over 4 units squared, okay? So what I want to point out is there's a bit of a relationship between the two of these here, okay? The ratio that we had used, where is that ratio? The ratio we had used, which happened to be root 2, okay? If you square it, you can use that as the ratio for area. Sorry, I forgot the word. So in this case here, for instance, if I want to go up, so remember when we were going in the upwards direction, we were multiplying by the value of 2, and we were going this way, we were dividing or multiplying by a half. If you want to find the relationship with squared, so for area, we actually just take that ratio, which is 2, and we square it. Same idea here, and square it. So for power of 2, that ends up being multiplying by, sorry, it was root 2, it wasn't 2. I was going to say, that doesn't make sense. There we go. When you square root 2, you get the value of 2. And when you square 1 over root 2, you get the value of 1/2. And if you take a look at that, 1 over 4 times 2 will actually give you 2 over 4, which is the 1 over 2. So that gives you that value. And if I want it to come down, 1/2 times 1/2 gives us 1 over 4. Okay, so that's the relationship between area and similar triangles. I don't know if that'll be part of what you guys needed to know, but it's, sometimes they pointed out that is sometimes something they'll go over when talking about similar triangles.
Right.